Hi, YouTube family. Welcome to Concept in Medicine. We are back in the ECG series. Today we are going to be looking at the cardiac axis. Alright, so when we talk about the cardiac axis, it is also known as the QRS axis, and it represents the major vector of ventricular activation, which overall is the direction of the electrical activity of the heart. Then the question goes, how then will you determine the cardiac axis? So with regards to the determination of the cardiac axis, you should know that it's going to be dependent on determining the relationship between the QRS axis and the main leads of the ECG. In our previous ECG series, we spoke about the 12-leg ECG. That's the standard 12-leg ECG. I would recommend that you go back and watch that video. And that video is on my channel. Alright, so I'll do a recap of the limb lead using the ectoven triangle. So when we say ectoven triangle, you should know that the ectoven triangle is an equilateral triangle, meaning that the angle between it, they are equal, 60 degrees, 60 degrees, 60 degrees, and we know that the total angle or the sum of the angles in the triangle is equivalent to 180 degrees. So you take this as 60, 60, 60. And we know that the lead 1 is placed between the right arm and the left arm, and is moving the direction towards the left. So this becomes the lead 1. Then we know that lead 2 is placed between the right arm and the left foot, and is moving towards the foot. And we also know that the lead 2 is the most important lead on the ECG. Why? Because it follows in the direction of the conduction system of the heart. That is the sinoatrial node going down to the atrioventricular node, moving down to the bundle of His, and then through the bundle branches, that's the right and left bundle branches, and furthermore to the Purkinje fibers, relaying impulses to the ventricles for them to contract. I believe we can recollect that from our previous ECG series. Now, so this gives us lead 1, 2, and 3. And we know that lead 1, 2, and 3, they are bipolar leads because they are moving from a negative to a positive charge. Then the next limb lead, we know that we have 6 limb leads. We've talked about 3 already. The remainder 3 is going to be the augmented voltage leads. So we are going to have the augmented voltage to the left, augmented voltage to the right, and augmented voltage to the foot. So we have 6 limb leads. Now we are going to use the direction of these leads to construct a circle. We are going to use the direction of these limb leads to construct a circle. And when we construct the circle, we are going to be dividing the circle into angles. That is going to be in degrees. And based on that, we should be able to know the direction in which the overall conduction of the electrical activity of the heart will follow. And that will be the cardiac axis. Now, let's look at this. If we draw a circle like this, as you can see, the circle total angle is 360 degrees. So half the circle will give you 180, another half 180. Now, if you take the ectoven triangle, lead 1, you can see that the lead 1 is moving horizontally towards the left. So in that case, this becomes our horizontal line. You can see that they are parallel. So this becomes the horizontal line, as you can see. So this becomes our lead 1. And lead 1, meaning if you are drawing a circle and you are trying to move with respect to the angles, then you start from 0. And in this case, we know that the AVF, augmented voltage to the foot, or basically The electrons that you are going to be putting on the foot, they are going to be what? Positively charged. Why? Because the ground is a reservoir for positive charges. Okay, so we know that here is always going to be positive and down. That is why in this circle, if you work very carefully, the lower portion is in positives because it is what? Facing the ground. And if we are facing the ground, then we say they are positive. So this is lead 1, as you can see. Lead 2, look at the direction which is going. Lead 2 is moving in this direction. So if lead 2 is moving in that direction, if you should retrace this onto the center, you are going to have lead 2 here, which is going to move all the way here. But because we are looking at the direction to which the lead 2 is pointing, we are showcasing that direction. Only this and the other we are using a dot. Okay, so this become our lead 2. And lead 2 will be at what angle? Look, lead 2 here, you can see that is, with respect to the horizontal line, is giving us for 60 degrees. So in the same way, this is lead 1, and this is lead 2. And what will be the angle between the two? Is going to be 60 degrees because we said this triangle is an equilateral triangle, meaning each angle is 60 degrees. So you are going to have 60 degrees here, and it's going to be positive. Why? Because it is facing towards the ground. So we are having plus 60 degrees. Now, we move ahead and look at lead 3. Lead 3, as you can see, it is moving in this plane. And if you should trace the path of lead 3, what are we going to have? We are going to have this green line here. So this becomes lead 3. It becomes lead 3. Then we ask ourselves the question. If you look at lead 3, you can see that lead 3 in relation to the horizontal line, that will be the lead 1, is 60 degrees. So if we look at that carefully and we extend this line backwards, then you should know that the angle between lead 1 and the lead 3 will become 60 degrees. But that is not the direction of the lead 3. The lead 3 is pointing downwards. And if it's pointing downwards, if here is 60, and we know that the sum of the angles of a straight line is equal to 180 degrees. If the other side is 60 degrees, then the other side should be what? 120 degrees. And in this case, because it's pointing towards the ground, it will be what? Positive 120. And because this one is away from the ground, it is going to be what? Negative 60. Please, I believe you are making some good sense out of that. Alright, so that gives us V3. Now let's move on to augmented. Let's move on to the augmented voltage leads. We'll take the first one, AVL. If you look at AVL, you can see that it is bisecting this angle of 60. And if you are bisecting an angle of 60, what are you going to have? You are going to have 30 degrees. So you can see, this is where our basic arithmetic mathematics comes into play. If you bisect an angle of 60 degrees, then you have what? 30 degrees. So in that case, you can see that the lead AVL, that's augmented voltage to the left, and is pointing towards what? The left or right, but at a particular inclination. And if you trace this onto this, we are going to have what? AVL here. You can trace it backwards also, but we are looking at the direction to which each of the leads is pointing. So if that's the case, we said that if you bisect an angle of 60 degrees, you have what? 30 degrees. So we are going to have 30 degrees here. Why are we putting negative? Because it is facing away from the ground. It is facing away from the ground, and that will give us minus 30 degrees. Alright, the next one is going to be AVR, which we are not going to be using so much in our cardiac axis interpretation or the types of cardiac axis. So the AVR, you can see, is also bisecting the angle of 60. That will give us an angle of what? 30 degrees. And look at the inclination. This inclination is the same as what? This inclination. And if you are saying angle of 30 degrees, definitely, if you should look at this very carefully, if it's an angle of 30 degrees, if you add 30 degrees to this 120 here, that will give us what? Definitely, it is going to give us 150 degrees. So it tells you that the AVR will be at what? Which angle? 150. And because it's pointing away from the ground, it is going to be what? Negative. Because I believe we are making a whole lot of sense out of this. Then finally, AVF. If you look at ABF, it's pointing straight to the ground. What do we have here? 90 degrees, because it's straight, it's a straight line. And if you look at it very carefully, this will give us 90 degrees. And because it's towards the ground, we are going to have positive 90 degrees. So this is how we are going to get the various angles on this circle using the ectovent triangle. So the trick here is that all the straight line that you are drawing, it should give you 180 degrees. So if you have here 30, then it means that here should be what? 150. If you have here 90 downwards, upwards should be 90. That will give 180. But the only difference is that the charges will be different. If you are pointing towards the ground, you will be positive. If you are pointing away from the ground, you are going to be what? Negative. I believe we are making a whole lot of good sense. We are making a lot of good sense out of it. And you should also know that majority of the muscles of the heart is concentrated in the left ventricle. Because of that, the cardiac axis is normally oriented downwards and slightly to the left. Downwards and slightly to the left. Now let's look at that. Downwards and slightly to the left, meaning that the normal axis, that's the normal cardiac axis, is going to be between what? Look at it very carefully. It's going to be between angle minus 30 degrees and what? Plus 90 degrees. So if the angle, that's the cardiac axis, is falling between minus 30 and plus 90 degrees, then we'll say that is a normal axis. That is a normal cardiac axis. When the overall direction of what? Conduction of impulses, that is QRS axis, falls between the angle of minus 30 degrees and plus 90 degrees. As you can see in this area, then it becomes a normal axis. We are going to, after we are done with this, we are going to look at examples, ways of determining the cardiac axis using simplified approach and also using other methods. Okay. Now, if the cardiac axis to be deviated towards the left, then it means that what are you going to witness? You are going to have that axis falling between minus 30 degrees and minus 90 degrees. So that gives you the left axis deviation. And if it is a right axis deviation, the cardiac axis is going to be between plus 90 degrees and plus 180 degrees. Just look at it. If I should stand like this is my right, this is my left. This is my right, this is my left. Right? So if this is my right, then look at this angle very well. What is this? Right axis deviation. If this is my left, I raise it up. What are we having here? This becomes what? A left axis deviation. And the normal axis, as I was saying, the bulk of the cardiac muscle is concentrated in the left ventricle. That is why the cardiac axis is normally inclined or directed downwards and slightly to the left. Okay? Now, there's another type of cardiac axis, and that's going to be the extreme axis deviation. When we say extreme, extreme is when you have the cardiac axis falling between minus 90 degrees and minus 180 degrees. Then we'll say that that is an extreme cardiac axis deviation or extreme axis deviation. So we are going to be using a lot of approaches to understand or to determine the cardiac axis on an ECG. Okay, let's move ahead and look at such methods. Alright, so now let's look at the methods of determining the cardiac axis. There are three methods. We'll look at three useful methods, and after that, we'll look at some tricks also used in determining the cardiac axis. So there are three methods. We'll start with the quadrant method, where we are going to be using leads 1 and ABF. Then after that, we'll look at trim leg analysis, where we'll be, in addition to lead 1 and ABF, we'll be bringing into play lead 2. Finally, the isoelectric leg analysis, isoelectric lead analysis, and that one we'll be using a particular approach. So let's begin with the first one, that's the quadrant method. For the quadrant method, we said that we are going to be looking at what lead 1 and ABF. And if you remember very well, on the ectovent triangle, so this this is lead 1. This is ABF. ABF is coming this way. This is ABF. So it tells you that lead 1 is looking towards where? The left. Lead ABF is looking towards where? The ground. It's coming inferiorly. Whilst lead 1 is moving what? To the left. Now, to use the quadrant method, you will be looking at the QRS charge. If I say QRS charge, then look at the Ecg waveform. We are having, so this is our PQRXT. If I say QRS charge, it means that you should find the amplitude of each of the waves of the QRS complex. So if you look at Q, the amplitude will be from here to here. S, the amplitude will be from here to here. And R, the amplitude should be from here to here. So if you take the amplitude of Q, which is a negative wave, which we'll be looking at in our next series, it's negative because it's pointing downwards. It's negatively, the Q wave is negative because it's negatively deflected. Because it is negatively deflected, it is pointing downwards. Same applies to the S, it's a negative wave. But if you look at R, anything that is pointing upward here on an Ecg waveform is positive. So if we add the amplitude of the R wave and the amplitudes of the Q and S, you realize that definitely the R wave is far more taller than what? The combination of the negative Q and X wave. Meaning that this QRS complex will have a positive charge. Okay. So when we say QRS is positive, it means that you should add the amplitude of the Q, R, and S waves to see what the resultant charge is going to be. It's just like you having, let's take the amplitude of the R wave to be 20. Let's take the amplitude of the R wave to be what? 20. You calculated it, you got 20 millivolts. Amplitude of the Q wave, you calculated it, you get minus 5 millivolts. Amplitude of the S wave, you look at it on the graph which we're looking at in our next series, and you have it to be minus 10 millivolts. If you have these three, you realize that the resultant number will be what? Plus 5 millivolts. And what's the charge on that? Is positive. Meaning that QRS net charge is positive, and the QRS overall direction is what? Upwards. That's what we mean by QRS being what? Positive. Alright, so let's look at some examples. But before we look at the example, let me show you something. So in this quadrant method, when we say quadrant, it means you should divide the circle into 4 parts. Right? 4 parts. Then ask yourself, where does lead 1 points to? Definitely, it points towards what? The left. If you are using a Ecg Graph, it points towards the left. So if you divide this circle into 2 halves, that is in a sagittal plane, then you are going to have here as right and here as left. And where does the lead 1 points to? It points toward left. So anytime lead 1 is pointing to the left in this method, it means that the QRS complex is positive. The QRS complex is having a net charge being positive. The QRS complex is having a positive net charge. So if that is the case, if lead 1 is moving to the left, it means the QRS complex in lead 1 is positively charged. And that tells you that you should what? Shade the whole of this half. If you divide the second in the sagittal plane, where you have right and left, if the QRS complex is positive in lead 1, then you'll be shading the whole of what? This half. I believe we are getting that. Then if you come to lead AVF, which we know points towards the ground, you can see that it's pointing downwards. So in that manner, then you can divide the circle transversely, in a transverse plane, where you are going to have superior and inferior. Then you ask yourself, where does the AVF point to? Definitely it points inferiorly. So if that is the case, if the QRS complex is positive in lead AVF, then we are going to have shading being done in the what? The inferior half. So in this case, we are going to have this. assuming the QRS complex is negative in ABF, then instead of shading down, where do you go? You shade up because it is negative. If it is positive, it's assumed that it is moving in the same direction as what ABF. That is why we are shading the bottom half. If you take the lead one, if it is positive, it's assumed that it's moving in the same direction as the one. That is why we are shading the left-sided half of the circle. So after that, you look at where the shading bisects, where they bisect, where they merge. And if you look very carefully, you look at this very carefully, you realize that the red and the black, they are merging in this quadrant. If you watch very carefully, they are merging in it. So this becomes the axis of what? The deviation. This becomes the axis of deviation. Then you can map this onto the standard axis of deviation. And we know that for the normal axis of deviation, it is going to be from where? Minus 30 to plus 90 degrees. And we know for left axis deviation, it's going to be from minus 30 to what? Minus 90. This is left axis deviation, this is normal. Then the right will be between plus 90 degrees and plus 180 degrees, which is going to be here. Then the extreme axis is going to be between minus 90 and what? Minus 180, which we said. So you just have to map the quadrants onto the standard axis of deviation, the types, and that will give you your answer. Now let's look at the examples. Let's take the first example. The net charge of QRS complex in lead 1 is positive and in lead AVF is positive. What would be the axis of deviation? Assuming you are looking on ECG, you realize that the net charge of what? The QRS complex in lead 1 is positive and that in lead AVF is positive. What will be the axis of deviation? So in that case, we will draw our circle and as usual, in that case, we'll draw our circle, and as usual, we'll have our quadrant. We'll divide it into 4 parts. Okay. Now, what is the QRS complex is lead 1? It's positive. It means it should move in the direction of what? Lead 1. And what is the direction of lead 1? Is to the left. So it means that you'll be shading the left half of the circle. Okay, if you divide the circle in a sagittal plane, you'll be shading the left half in that manner. And that means that it's positive. If it were to be negative, then you will not shade this direction. You will not shade this side, rather you shade the other side. Then now, the ABF is positive. Where that the ABF points to bottom, inferior. So it means that you are going to be what? Should you divide the circle transversely, the lower portion should be shaded because that is where the ABF points. Then when you are done with that, and you find the point of intersection of the shading that you've done, and you will notice that the red and the blue shades are bisecting in these quadrants, And you ask yourself, this quadrant, where is it? It's between 0 degrees and what? Plus 90 degrees. And you ask yourself, if you map it onto the types of cardiac axis, you realize that the normal cardiac axis is between minus 30 and 90 degrees. And if you watch 0 and 90 degrees, where does it fall? It falls between what? Minus 30 and 90 degrees, meaning that this axis, cardiac axis, is what? The normal axis. Because I believe we understand that. Okay. Let's look at the next example. The QRS charge in lead 1 is negative, and QRS in the ABF is positive. What is the cardiac axis? Alright, or what is the axis of deviation or the cardiac axis? So in that scenario, we draw our circle, divide into 4 quadrants. Then now, what is the direction of the QRS in lead 1? It's negative, meaning that it is going to be moving in the opposite direction of the usual lead 1 direction, which is to the left. So in this case, we are not going to shade the left half. Rather, we'll be shading the right half because it is what? Negative. So we shaded this as what? The QRS charge in lead 1. Then we look at the ABF. What is the QRS charge? It is positive, meaning that definitely you are going to shade the bottom half. And if you shade the bottom half, where do these shading this side, you know that it is mapping onto the right axis deviation as we initially stated. So you can see that the right axis deviation, the cardiac axis is between plus 90 degrees and plus 180 degrees. And what are we having here? We are having plus 180 degrees. I believe that makes sense to you. Okay. Let's move on to the third example. For the third example, we are having the QRS charge in the bond to be what? Positive. Then we have the QRS charge in the ABF to be what? Negative. And if we should draw our circle and divide into the quadrant, lead 1, the QRS to positive, meaning that we should be shading the half here, pointing to the left. Then QRS in the AVL is negative, meaning that we cannot shade the bottom but rather the top. And if we shade the top, look at it very carefully. Where do they bisect the shading? They bisect in the quadrant of a quadrant between 0 degrees and minus 90 degrees. And if you are looking at 0 degrees and minus 90 degrees, you will note that it is going to be overlapping between the normal axis and the left axis, because the left axis is between minus 30 degrees and minus 90 degrees, while the normal axis is between minus 30 degrees and plus 90 degrees. And if you watch very carefully, the bulk of the location is inclined to the left axis deviation, and the axis deviation is going to be what? The left axis deviation. I believe we are making sense out of that. Then now, the last one, QRS in the one negative, QRS in the ABF negative. Then, where are we going to be shading? If we take the one, then definitely we are going to be shading the opposite side in blue. If we take the ABF, instead of shading the bottom, since the charge is negative, we shading the top in red. Then you ask yourself, where does the red shade in the blue shade bifurcate? Where do they bisect? You can see that they are bisecting in this quadrant. And if you look at that quadrant, where is it? Between minus 90 and minus 180. And we know if the cardiac axis is falling between minus 90 and minus 180, then that is an extreme axis deviation. That is an extreme axis deviation. Alright, to add something more, if we take the third example, we realize that, as we are saying, it is both left axis deviation and what normal axis deviation, because the angles are bisecting. Because I told you the normal axis deviation is between negative 30 degrees and plus 90 degrees, whilst the left axis deviation is between minus 30 degrees and minus 90 degrees. So you can see that they are bisecting. But it's more of what? A left axis deviation. But we cannot be so sure. We cannot be so sure about that. Because of that, it is preferential to say it's what? A possible left axis deviation. It's preferential to say a possible left axis deviation. Okay. So if you have scenarios like that, then to be sure whether it's a real left axis deviation or it's a normal axis deviation, then we'll move to the second method. We use the second method where we are going to employ, in addition to lead 1 and ABF, lead 2. Let's have a look at that. Alright, so let's look at the 3-leg analysis method. That is using lead 1, 2, and ABF. Initially, we were using 1 and ABF for the quadrant method. This time around, we are adding lead 2 to make our analysis better. So let's take a look at what I mean by that. So lead 1 and lead 2, lead 1 and ABF is clear from the quadrant method. Now lead 2, how do we get lead 2? If you look at lead 2, you can see that lead 2 is here from the ectoven triangle and is pointing downwards. So if lead 2 is pointing downwards, it means that it is moving towards the ground in a positive direction. So if the QRS complex net charge is positive, then it means that it should also be pointing downward. So if you should draw the circle, we know that if we are looking at the one, we use like this. If the QRS complex is positive in the one, then where we go? We are moving towards the left, so it's going to be here. If it is positive in the ABF points to the ground, so we divide it in this direction. If it's positive, then we are shading here. Then, what of lead 2? Lead 2, then we have to use a diagonal line. What's the diagonal line going to look like? We are going to move in this plane, in this plane, in this plane. So it means that if QRS complex is positive in lead 2, if you ask yourself, where does the lead 2 point? They point downward. So that is where you are going to shade. So if QRS complex is positive in lead 2, then you are going to shade here. Completely. So it means the circle will become like this. If QRS complex is positive in the 2, then you are shading the downward aspect, not the upper portion, because the 2 points were downwards. If it is negative, then you shade here. The same way we were talking about the 1. If it is positive, then where do you shade? You shade the left side. ABF, if it is positive, where do you shade? You shade the bottom side. So this is ABF, positive QRS. And if it's negative, you shade the opposite side. This is B1, positive QRS. If it's positive, you shade the left side. And this is B2, positive QRS. If it's positive, you shade the bottom side. I hope this is clear. So we are going to be using this understanding to get the whole ideology using the 3-date analysis approach. That is B1, ABF, and B2. Okay, so let's look at the first example. QRS complex net charge is positive in B1, positive in B2, and is positive in the ABF. So we draw our circle. So we'll start with the first one. We'll use the D2 finally as the final one because we're using D1 and ABF in a quadrant method. So we'll stick with that and we'll finish it up with the D2. We know that if it's D1, it's positive. So where are we shading? Definitely we are shading this. Then lead 2 is positive, but we'll do that lastly. Lead ABF is positive. How do we shade that? If it is positive, definitely we are going to shade the bottom. Then finally, lead 2. We know lead 2 is supposed to be what? Diagonal. If it's diagonal and it's positive, what do you shade? You shade the bottom because lead 2 points what? To the bottom. So we are going to shade the bottom. Then you ask yourself, where in the circle does the 3 shading, where do they match? If you look here, we have blue and red. If you look here, we have red and black. But if you look here, you have what? Red, blue, and black. So that becomes our zone. So we are going to have this zone being our axis of deviation. So this is going to be the axis of deviation. Okay? And if you look at this very well, you know that it is between 0 and plus 90. And 0 and plus 90 degrees, that gives you what? A normal axis of what? Deviation. This is how we get that. Does that make sense? Can you see it's easy? Can you see it's understandable? Now, let's move to the second example. QRS complex in lead 1 is positive, lead ABF negative, and lead 2 negative. So in that scenario, what are we going to do again? So in this example, what are we going to do? We'll draw our circle. The first one we said lead 1, QRS is positive, so what are we going to have? Definitely, we'll have the shading to the left because it's positive. And the next one, the ABF, what are we having? It's negative. So if it's negative, what do we do? We go like this. Negative, it means we are not going to shade bottom, we will go up. And finally, lead 2. What do we have there? We have what? Negative. And if it's negative, where do we go? Where do we incline our line? Our line is going to be inclined in an oblique pattern, and it's negative, so we cannot shade down because the 2 normally point downwards, so we are going to shade up. And you should be asking yourself, which area in the circle that's the three calyx mesh. You realize that well? It is here. It is here. So you can see that this is minus 30 minus what? 90. And if the angle of deviation is in this zone, then we know that it's what? A left axis deviation. And this is classical left axis deviation. And for that matter, we call it pathological what? Left axis deviation, as you can see. So the next example, we have the QRS complex chart in the 1 negative, and the ABA positive, and the 2 positive. So what do we do? The first thing is here, as we have here, it means that we are going to be shading this side, the right side of the circle, which you have debiting what? That the QRS complex in the 1 is negative. Then the next one is the ABA positive. What do we do? It means that if it's positive, we are going to be shading the bottom aspect, which we did here with the red ink. Then the 2, we draw our diagonal line, our oblique line. What we have there is positive, so we are going to shade the bottom aspect. And if you are shading the bottom aspect, ask yourself, in which area of the circle are you going to have the 3 shades merging? And you can see it is here. You have green, red, blue. And if you look at that angle, that will give minus 95. This angle will give you plus 90 and plus 180. And it falls within the zone of the right axis deviation, making it a right axis deviation. Then, finally, another example is you have the 1 negative, the 2 negative, the ABF negative. The 1 negative, you know that we should shade the right side of the circle. The ABF negative, you should know we should shade the upper portion of the circle, which is down with the red ink. Then, the 2 negative, we draw our diagonal line, meaning that we should be shading in that aspect, we are shading with green. As you can see here, we are shading with green. And if you are shading with green, what are we having? You can see the area where the red, blue, and the green mesh is within this zone, as you can see. And this zone is what? Minus 90 degrees and what? Minus 180 degrees, giving you extreme axis of deviation. Extreme axis of deviation. And finally, we have QRS complex in the 1 being positive, the QRS complex and the ABF being negative, and in the 2 is epiphasic. Epiphasic. Epiphasic means that it's equal. If we add the amplitude of the Q and the S wave, and you equate it to the amplitude of the R wave, it will be equal. That's what we call epiphasic. So you are going to have something like this. If you add the amplitude of the Q and the S, it should give you the amplitude of what? R. That's what we call epiphasic QRS complex. So in that scenario, what do we have here? Look, in that scenario, we are going to have the 1, QRS is what? Positive, so we are shading with blue to the left side. The ABF, PRS is negative, we are shading upwards with what? The red ink. Then, the 2, we know we should draw a diagonal line, but again, it's epiphasic, so we cannot shade anywhere per se. It's epiphasic, it is neutral. So in that case, we realize that once it's epiphasic, they are going to be looking in the direction here and here. Okay? So that will give you what? It is going to give you what? The angle of deviation falling between 0 degrees and what? 30 degrees. 0 degrees and minus 30 degrees, sorry. 0 degrees and minus 30 degrees. And if you have the angle of deviation, that is the cardiac axis falling between 0 degrees and minus 30, standardly, it is regarded as what? A normal axis. A normal axis or normal cardiac axis. But again, we can also describe that perfectly as a physiological left axis deviation. It is physiological. I believe we made a lot of sense out of that. Alright, so let's move ahead and look at the last method. Alright, so let's look at the last method. That's the isoelectric plate. So with isoelectric plate, I would like you to have a look at the various axes of deviation in addition to the normal axis of deviation. You know that the normal axis of deviation is from minus 30 degrees to what? Plus 90. Left axis deviation minus 30 to and what? Minus 90. right axis deviation is between plus 90 and what? Plus 180. Extreme axis deviation is between minus 90 and minus 180. Take note of that. Please take a look at this very well. Take a look. A critical look at it very well. Critical look at it very well because we are going to be using this in our explanation. Alright. So now let's have a look at this Ecg graph. Looking at the Ecg graph, you will notice that you have the isoelectric lead being what? The lead. AVL. Why am I saying that? If you look at the AVL, you realize that the amplitude of R wave and the S wave, they are the same, so they cancel out. That makes it an isoelectric or epiphasic lead. AVL. Epiphasic QRS. If you look at the QRS component, you realize that you have only R wave and the S wave. And the R and the S wave, they are cancelling out because they are equal in amplitude. We know S wave is negative, R wave is positive. So that will give you 0. So that becomes our isoelectric lead. So once you determine your isoelectric lead, what is that lead? It's AVL. And if we look at AVL, where does it point to? So you can see that AVL is pointing in which direction? Minus 30 degrees. And anytime you have the location of the isoelectric lead, which is AVL, which is given as minus 30 degrees, what are you supposed to do? You are supposed to add plus or minus 90 degrees to it to know the location of your cardiac axis. And before you do this, you should have found all the positive leads, that is, the leads which have QRS positive in them. And when you finish doing that, what do? You will now add plus or minus 90 to the degree of what? The isoelectric lead. And minus 90 plus 90 will give us what? Plus 60 degrees. And minus 30 minus 90 will give us what? Minus 120 degrees. Minus 120 degrees. So it means that in that case, the axis of deviation is going to be between plus 60 degrees and minus 120. The axis of deviation, the cardiac axis is going to fall between plus 60 degrees and minus 120 degrees. Now let's go back and look at the Ecg graph. So looking at the Ecg graph, you will notice that there is in lead 1, the QRS complex is positive. And what's the direction of lead 1? You know that is what? 0 degrees. If you look at lead 2, the QRS complex is what? Positive. What's the direction of the QRS complex? Is plus 60 degrees. Then again, AVF, the QRS complex is what? Positive. And again, what is this direction? It's plus 90 degrees. So it tells you that those things that I mentioned on the Ecg graph, they are having positive QRS complex. And we should know that the axis will be lying between 0 and plus 90 degrees. That is if we should draw, which we will do right now. Okay, so let's have a look at that. I hope you've studied the Ecg graph. So we know that the cardiac axis is supposed to fall between what? Plus 60 and minus 120. And from the Ecg, we realize that lead 1, the QRS is positive. Lead 2, the QRS is positive. Lead AVF, the QRS is positive. That's what we realize. And what is lead 1? Where is the direction of lead 1? Where is it? Definitely it's 0 degrees. It's 0 degrees. Lead 2, where is the direction? Lead 2, where are you? Plus 60 degrees. As you can see, lead 2. This is lead 1. Then lead AVF, where are you? You can see it's where? Here. That is what? Plus 90 degrees. Now let's draw our circle. So divide the circle into what? 4 quadrants. We know that this is 0 degrees. And definitely we know that this is lead what? 2, which is 60 degrees. This is lead 1, which is 0 degrees. Then we have the AVF, which is 90 degrees. Okay? Then we know our lead 1 is 0 degrees, lead 2 60 degrees, lead AVF 90 degrees. Meaning that it tells you that we are going to be having your axis, the cardiac axis, located between what? Here and here. That will be 0 degrees and 90 degrees. But again, if you watch very carefully, we are saying that the cardiac axis, after we finish locating the leads which have positive QRS complexes, we know our isoelectric lead from the ECG to be lead what? AVL. And what is AVL? AVL is what? Minus 30. And to get your cardiac axis, you have to add or subtract 90 degrees. And if you should do that, it will give you what? Minus 120 degrees or plus 60 degrees. It means the cardiac axis is going to be either plus 60 or minus 120. But how do you locate where the cardiac axis could be? It could just be one of them. Either it's plus 60 degrees or it's minus 120. But how do we find where it could be? Either plus 60 degrees or minus 120. That is where you find the leads with what? Positive QRS complex. And we found them to be lead 1, lead 2, lead AVA. We know lead 1 corresponds to 0 degrees. Lead 2 corresponds to what? Plus 60 degrees. Lead AVA corresponds to what? Plus 90 degrees. Meaning that our cardiac axis can only be situated between 0 degrees and 90 degrees. 0 degrees and plus 90 degrees. Then ask yourself, the value that we got, plus 60 degrees and minus 120 degrees, which of them will fall within this range? Definitely, and it's going to be what? Plus what? 60 degrees. Meaning that our cardiac axis is falling where? At what? An angle of what? Plus 60 degrees. And if you work very carefully, we know that the normal axis, as a normal cardiac axis, fall between minus 30 degrees and plus 90 degrees. And if you look at plus 60 degrees, it falls within this range. You can see that it falls within this range. And that tells you that the cardiac axis is a normal one. I believe you've gotten an understanding. I know this particular third method is a bit complicated. So it is usually advisable that you stick with either the first or the second one. I'm going to be showing you some simplest way to also arrive at the cardiac axis. Let's have a look at them. Alright, so let's have a look at another simpler method to determine the cardiac axis. So here I listed the simplest approach. So if you look at the QRS complex, okay, and it's positive in lead 1 as well as lead 2, know that that is a normal axis. If we take QRS complex, the net charge negative in lead 1 and it's positive in the AVF, know that that is a right axis deviation. That is a right axis deviation. And we know that the normal axis deviation, the normal axis, we know that normal axis lies between minus 30 and what? Plus 90 degrees. And we know left axis deviation. No. We know that the right axis deviation, as we are saying, it lies between plus 90 degrees and plus 180 degrees. And I'm saying that if the QRS complex is positive in lead 1 and it's negative in lead 2, know that that is the left axis deviation. And we know the left axis deviation, the axis lies between minus 30 and minus 90 degrees. Then finally, if the QRS complex is having a negative charge in leads 1 and AVF, then you should know that the cardiac axis is experiencing what? An extreme deviation. That's what we call extreme axis deviation, which lies between minus 90 degrees and minus 180 degrees. I hope this is simpler. This is direct. But the other methods are also very good, especially the second approach. That is the 3D analysis is the best. You want to use that always. Now let's have a look at another simpler way of determining the cardiac axis on an ECG. Alright, now let's look at another method to simply or easily identify the direction of the cardiac axis. This one we are going to be using the 1 and the 3. So you are going to be looking at the neck chart of the KRS complex which we discussed. So if you look at the 1 and the KRS complex is positive, and you look at the 3 and the KRS complex is negative, it means that they are moving away from each other. And if you meet at a point and you are moving away from each other, we say you are leaving, you are left, you have left. If you are leaving, we say you have left. So once they are leaving, they have left. So that becomes a left axis deviation. So I hope you noted that left axis deviation. They are moving away from each other. They are leaving. They have left axis deviation. Then if you come to lead 1, and then lead 1, the KRS complex is negative. And you come to the 3, the KRS complex is positive. And it tells you that what? They are converging, they are meeting, they are kissing, they are coming close to each other, they are meeting at the point. Means that they are getting it right. They are getting it right. If you have two lovers who are in love and they are kissing, it means that they are getting it right. So that makes it the right axis deviation. So the right axis deviation, the KRS complex in the 1 and the 3 will be kissing. Then the left axis deviation, the KRS complex in the 1 and the 3 will be moving away from each other. They are leaving, they have left. I believe that makes a lot of sense to you. Now let's look at the causes of the various axes of deviation. So let's take the first one, causes of right axis deviation. It could be a normal variation. It can also be a right ventricular hypertrophy, which is one of the common causes of what? Right axis deviation. We can talk about a ventricular ectopy. Okay, we can also think of a left posterior fascicular block. You can also think of a lateral XT segment elevation, myocardial infarction. You can think of pre-excitation syndromes. You can also think of hyperkalemia being a cause. Then we can also think of a Wolff-Parkinson-White syndrome, where you are going to have a slave upstroke of the QRS complex. Then you can also think of what? Dextrocardia, where the apex beat may be found in the right feet intercostal space, mid-clavicular line. And it's usually associated with the Cartagena syndrome. Then we move to the causes of the left axis deviation. Again, normal variation. You can think of left ventricular hypertrophy, and you can also think of a left anterior fascicular block. We can also think of a left bundle branch block. Then we can also think of ventricular ectopic with an inferior myocardial infarction, pre-excitation syndromes, and also congenital heart disease with pulmonary atrial septal defect. Then the question goes, what are the causes of the extreme axis deviation? For that one, they are simple. You're thinking of ventricular ectopy. You're also thinking of ventricular tachycardia. Then you can also think of a very uncommon term. That is what we call accelerated idioventricular rhythm. AIVR. Accelerated idioventricular rhythm can also be a cause of extreme axis deviation. We can also think of hyperkalemia, and finally, severe right ventricular hypertrophy. That is where we bring the lesson on cardiac axis to an end. I believe that you've found a basis, a ground for understanding these concepts. Kindly make sure to subscribe, like, share, and also comment the concepts you would like to see in my next video. This is the ECG series. My name is Dr. Del, and this is Concept in Medicine. See you in the next ECG series. Bye-bye.